Are you buying a new electron microscope and worried that either AC or DC magnetic fields could negatively impact your tool's image? Or are you building a new facility or renovating an existing one and worried that the design decisions that you make now could have negative impacts and degrade instrument performance long into the future? If that's the case, then this video is for you. We're going to talk to you a little bit about both AC and DC magnetic fields, some theory behind it, common sources. We're also going to talk a little bit about mistakes and pitfalls we see customers make, and then strategies to avoid them. So we're going to start today by talking about AC magnetic fields. So AC magnetic fields are the magnetic fields generated by the electrical infrastructure inside and outside of a facility. So in the US, AC magnetic fields typically occur at 60 Hertz, while it's 50 Hertz in Europe and some other countries. AC magnetic fields can generally be separated into three overarching categories. So the first category is a net current. So a net current occurs when there's a wire with a current in it without a return, or an imbalance in currents between the positive and negative, resulting in a net current through that cable. The second type of magnetic field is called a dipolar field. And a dipolar field occurs when there's a positive and negative separate to enter a piece of electrical equipment, such as a branch panel or distribution panel. The third type of magnetic field is the magnetic field generated by current through a coil, such as in a transformer. These three different categories of magnetic fields behave differently with how they degrade over distance. A net current generally degrades at roughly one of the distance from the source. The dipolar field, the separation into a branch panel or distribution panel, that degrades at roughly one of the distance squared, while a transformer degrades at roughly one of the distance cubed. We've done a lot of analysis and testing in facilities. That's not exactly correct, but it's generally accurate for our discussion today. The result is that these different magnetic fields, even if they're the same at the source, they can be drastically different at the electron beam column, which is what matters the most. And so when we do our EMI modeling services for an engineer or a customer, we often provide results that are drastically different than what the electrical or design team was expecting when they gave us the plans to analyze. So let's look at common sources of AC magnetic fields inside the laboratory. So the first and obvious source is wiring and outlets inside the walls. Wiring and inside the walls for new construction or renovations where there's a complete tear back of all existing electrical equipment and new wiring has been installed. For these types of installations, AC magnetic fields in the wiring of the rooms is not that problematic, particularly if there's care taken for which type of conduit to run the wiring in. That's because to do the wiring to code, you're going to have a balance between positive and negative, and so you don't have the net current issue that you have in older type buildings. For renovations or for buildings that were built in the 60s, that have been owned by rented by 7 different companies, and each one of them has done a renovation to meet their needs. Those renovations aren't always up to current electrical standards. These facilities often have significant magnetic field issues generated by wiring and outlets in the facility. And so these wirings, with the electricians or whoever put in the wiring, they could have taken shortcuts or not done things exactly as you should, resulting in net current. And as we just discussed, net current is really problematic, and this can result in serious magnetic field issues for your lab. The second type, and this was more of a problem in the past than it is now, but is lighting. In the 80s, 90s, where magnetic ballasts were used for fluorescent lights, these magnetic ballasts were a significant magnetic field source and caused significant issues for imaging performance. And if you put an electron microscope in a room with these old school magnetic ballasts. Nowadays, with the advent of modern LEDs, this isn't as much of a problem as it is before. We hear customers kind of over-index on this because the historical experience with magnetic ballast lighting. But if you use modern LED lights, this typically isn't an issue. The third really common source of magnetic fields we see inside a lab is the racetracks and power strips that you see run around labs. These are often over workbenches, so users can plug in their laptops or equipment, electrical equipment, or instruments they need to do their experiments. These raceways and power strips are very problematic, particularly the cheaper ones. Inside the strip, you see separation of positive and negative. The wiring is not always high quality. These strips and raceways are often extremely problematic for electron microscopes and other imaging tools inside a facility. It's something we recommend customers avoid when they're designing their labs. So looking at AC magnetic field sources outside the lab, outside the room, you have several sources which are obvious, right? You have the electrical rooms, which have branch panels, distribution panels, transformers, switch gears, etc. We've already talked that these are high magnetic field sources, particularly when they have high loads and therefore high current. Obviously, you don't want to put sensitive TEM right next to an electrical room. However, what's often overlooked is if you have two electrical rooms on either side of the facility, if you have a feeder or busway going between the two, and that feeder or busway happens to go through the slab or overhead or on the adjacent wall to your electron microscope or e-beam lithography room, these feeders and busways are problematic and often not noticed by customers until you start taking EMI measurements and doing some further investigation. This is something we look at closely. If we do our modeling, we look at the magnetic field generated by the electrical rooms, but also the feeder conduits that feed between the two. In addition to inside the building where you have the feeder conduits between the electrical room, you also need to look at how power gets into the building through like the interconnect. We've seen examples where customers spend an enormous amount of time, effort, and money designing their facility to the highest EMI standards, while they'll have their TEMs located in a place where they'll have the main power for the street run underground 30 feet away in PVC conduit. And so PVC conduit provides absolutely no attenuation whatsoever. And so if that PVC conduit is providing power to the entire street, it obviously has a lot of load, therefore a lot of current, as a significant AC magnetic field source. So when we do our AC magnetic field modeling and we look at doing our design consulting for our customers, we look at model obviously the obvious sources which we discussed, like in the electrical room, etc. But we'll also look at how power goes from one electrical room to the other and provide suggestions on shielding, routing, and instrument placement. When you're talking about DC magnetic field sources inside the laboratory itself, you're almost always talking about the movement of large ferromagnetic objects, and that's steel doors. So that's steel doors to the laboratory, steel doors to the chase, steel doors in the hallway outside the laboratory. And so because these doors are large and steel, when they open and shut, they cause Earth's magnetic field lines to bend. They're in relatively close proximity to the column, and so it results in a beam shift, which is problematic. It results in image distortion and bad data. So VEC recommends using solid core wood doors basically throughout your laboratory and avoiding using steel doors whenever possible. Why do customers use steel doors? Well, steel doors provide excellent sound transmission loss STC ratings that keep noise outside of the laboratory. Electron microscopes are very sensitive to acoustic noise, but we view that the benefits of keeping the noise out doesn't outweigh the risks of changes in DC fields at the column. Other changes in DC field sources, movement of large ferromagnetic objects, you can look at swivel chairs. If you move around on a swivel chair too close to the column, that can be problematic. But honestly, we see customers almost go too far trying to keep steel or ferromagnetic objects outside the room. So, we'll see customers write in the specification that there can't be any steel or metal on the hardware to the cabinets, the lab cabinets, etc. You could probably induce some sort of imaging issue if you open and shut a steel door to a lab cabinet too close to the column. But our view is that behavior is not consistent with how users act when they're trying to conduct high resolution imaging. When a high resolution imaging is occurring, everyone's typically still, quiet, and focusing on being as still as possible and quiet as possible to create the best resolution possible. That is not a time in which people are digging through the cabinets looking for a cup of coffee or to prep the next sample. For sources inside the laboratory, generally speaking, stay away from steel doors. So when we're talking about DC field sources outside the laboratory, we're also looking for movement of large ferromagnetic objects. So if you are adjacent to a loading dock with significant forklift traffic, that can be an issue. If your lab space is adjacent to an elevator bank, this is a problem. As the elevators move up and down, they cause large shifts in DC fields. This is a very common source that we see, and something that you should avoid, or you need to mitigate or address if it's not possible to change the microscope location. Another consideration is if you're next to a parking lot or a road, vehicular, truck traffic, etc. As those drive by, they can cause DC field shifts as well, which is problematic and something we've seen in the past. In addition to the movement of large ferromagnetic objects, you also have equipment in a facility that can impact your lab space as well. So NMR machines, MRI machines, etc. Things like that can be problematic. NMRs, when they're operating in a steady state, they typically don't cause any problems, but as they ramp up and ramp down, they can result in significant beam drift throughout the duration of that ramp and are really problematic. Another consideration is if your facility is located in a city with subways and above ground trams, in addition to those being large metal objects moving through space, which is a problem, they also pull a significant amount of currents to power them. That current pull, both for the train as it's passing and for trains down the track that you can't see, that current pull can create very large DC field shifts, which are problematic and can be measured hundreds of yards away from the source. So something we see quite frequently in our customers in cities. So we've talked quite a bit about both AC and DC magnetic field sources inside and outside of laboratories. And now I want to discuss what a project with VEC looks like if you wanted to engage with us in your new facility. The first thing we do almost always is a baseline survey, site testing to understand what the ambient AC and DC magnetic fields are in your space. It doesn't matter if it's an empty shell of a building, if the loading is going to change completely, a space that's designed for one thing that's going to be completely changed. It's still important to understand what we're dealing with before we get started. We talked a lot about AC and DC magnetic field sources outside the building. We want to make sure we quantify those and don't miss those during our design phase. Next we would do is we would do a detailed AC EMI model based off the electrical plan provided by the electrical team and the design team. This isn't a one-way process where the electrical team gives us a design and we say it looks good or not and issue a report. It's a collaborative back and forth where we take the initial design, we do a model, we then recommend solutions that can be implemented in the design, and then issue a final report once we feel comfortable that we've optimized the design for the client and the instrument performance. For DC magnetic fields, we have a large database, DC magnetic field sources that we leverage to make sure that we quantify and limit the introduction of DC field sources into the new facility. At this point in the project, it's VEC's goal that we have a design in place that we feel confident that will meet project requirements and instrument specifications without any additional modifications or remediation. However, sometimes additional mitigation solutions are required to meet instrument requirements. You could have an external source that we quantified in the initial site survey that the design team has no impact on. There could be project requirements such as tool density that prohibit us from meeting the specifications for all instruments. Or the customer could want to future-proof the space against unforeseen changes in the environment that are not considered or unknown now. VEC has a couple different options for how to move forward to implement mitigation solutions if additional mitigation is required. VEC's modeling software has the ability to model passive shielding, AC passive shielding. VEC does not install AC passive shielding, but we can quantify the benefits and make introductions to passive shielding vendors that we've worked with in the past, and we can collaborate with on this project. VEC also sells Spicer AC and DC magnetic field cancellation systems, and we can design and install a magnetic field cancellation system based off room layout, ambient conditions, and unique tool specifications. So if you decide to go down that route with us, you should feel confident that we would design and install a system based off of a deep understanding of both ambient lab conditions, project designs, and project requirements. So I hope this video was helpful. If you have any questions, you feel free to reach out to us at www.vibeng.com. We have a lot of additional information on the website, and we look forward to working with you on your next project. Thanks.